Okay, so let us now start the set of exercises after this section on homomorphisms. Exercise 1. In the following, verify if the mappings defined are homomorphisms. And in those cases in which they are homomorphisms, determine the kernel. Okay, so let us see what the groups are and what the functions are. In part A, G is the group of non-zero real numbers under multiplication. G bar is G and the function phi is defined to be this for all x in G. That is, the function phi maps G into G bar and the formula for the function is this. Then in part B, G and G bar as in part A, same groups, but the function this time is the one that maps x onto 2 to the power x. In part C, G is the group of real numbers under addition. G bar is the same as G and the function phi maps x onto x plus 1. For all x belonging to G. Then two more parts are there. In part D, the groups G and G bar are the same as in part C, and the function phi maps x onto 13x for all x belonging to G. G is in part E. G is an abelian group. g bar is the same as g and the function phi is defined like this. For all x in g. So for each one of these functions we have to decide whether it's a homomorphism, and if it is, then we have to find its kernel. So let's start the solution. So in part A, both the groups are the group of non-zero real numbers under multiplication, and the function is this. For two elements x and y in G, we have phi of xy equal to xy whole square. Since x and y we are in the system of real numbers, so xy whole square equals x square times y square. So, and x square is phi of x, y square is phi of y. So phi is a homomorphism. Now we want to determine the kernel of phi. Since, keep in mind that both g and g bar are the multiplicative group of non-zero real numbers. So there the identity element is the real number 1. So since phi of 1, so the kernel will consist of precisely those non-zero real numbers whose squares are equal to 1. So since phi of 1 is equal to 1, and okay, in fact we can determine the kernel somewhat. We don't have to write this many things, since the only solutions to the equation x square equal to 1 in the set of real numbers are -1 and 1. The kernel of phi, which we already we have decided on this notation, k of phi, k phi means the kernel of phi, is equal to this. Okay, so it is this subgroup of the group of non-zero real numbers under multiplication. Part B. Before showing that some function is a homomorphism, you have to first of all guess that it's actually a homomorphism or not. Then you proceed to show the thing accordingly. In this case, we can clearly see this calculation before we even write it. It's that easy. So we just simply proceeded to show that it's a homomorphism. In the second case, however, we can pretty much guess it's not going to be a homomorphism, because you see, if you try to calculate here also, g and g bar are the same group, non-zero real numbers under multiplication. So if you try to calculate 2 to the power xy, that is, if you calculate phi xy, you get, whereas if you on the other hand calculate phi x times phi y, then that is this, and these two things in general are not equal for all x and y. So phi is really not a homomorphism, but a much better way of saying that is this. We know that one of the properties any homomorphism has is that it maps the identity element of the domain group onto the identity element of the second group. And in our case, both the identity elements are equal to the real number 1. So since phi of 1 is not equal to 1, the phi is not a homomorphism. And that is why there is no question of kernel. Same is the situation in part C. In part C, both the groups are the group of real numbers under addition, and the function is this. So in both the groups, the identity element is 0, is the real number 0. Since phi of 0 is equal to 1, which is not equal to 0. So phi is not a homomorphism. Okay, so now we come to part D. In part D, it will be a homomorphism. Here also we have the both the groups are equal to the additive group of real numbers. For any two real numbers, we have phi of x plus y. Keep in mind that now the binary operation is addition in both the groups. Using the left distributive law that is true in the system of real numbers, this becomes this, which is phi of x plus phi of y. Thus, phi is a homomorphism since the equation 13x equal to 0 has the only real solution. Real solution means solution in the system of real numbers. X equal to 0, we have that the kernel of phi has only the real number 0. So in this case, the kernel is the trivial group in the additive group of real numbers. And this in particular, although we have not been asked to say anything more than this, but still we note that because the kernel is this, the mapping phi is 1 to 1. It's an isomorphism. Finally, in part E, we are given G is an abelian group. G is any abelian group. G bar is G and the function is this. For any x and y in G, we have since we are in an abelian group, so this power will be equal to x to the power 5 times y to the power 5. So this is 5x y. Hence phi is a homomorphism. In this case, since we don't really know what the abelian group G is, so the most we can say in this case about the kernel is this. The kernel is the set of those elements in G whose fifth powers are equal to the identity element of G. So that concludes the solution. Exercise 2. Let G be any group small g a fixed element in G. Define a mapping phi from G into itself by phi x equal to Gx G inverse. Prove that phi is a homomorphism of O. It's not just a homomorphism, it's an isomorphism. And that too an onto isomorphism of G to itself. The mapping defined is clearly well defined, because we have the only thing we have used in defining this mapping is the binary operation in G, which as a mapping itself is well defined. So that's why this mapping is also well defined. Okay, so let us now first show that phi is a homomorphism. We will then show that it's onto, and then it's an isomorphism by showing that the kernel is the trivial group consisting of only the identity element. So first, homomorphism. For any x and y in G, so this is a general type of isomorphism and onto isomorphism, because the group we have is any group where we have fixed an element G and we are defining the mapping like this. So we have phi of xy equal to Gxy G inverse. Now note carefully that this element can be written as Gx G inverse Gy G inverse. This G inverse and G cancel out, leaving us with Gxy G inverse. But this is equal to phi x, phi y, hence phi is a homomorphism. Next we see that phi is onto. So for ontoness you take any element in the second group, which in this case is the same as the first group. So let H be any element in G. Then the element G inverse HG belongs to G such that its phi image becomes equal to G inverse HG G inverse, which if you see becomes equal to H. So we have realized any element in G in the second group as the phi image of some element in G, the first group. So phi is onto. Next, let Z be any element in the kernel of phi. Then GZ G inverse, which is phi of Z, is equal to E, and hence Z, which can be written as G inverse G Z G inverse G, also becomes equal to E. G inverse EG is equal to E. This shows that the kernel of phi is the trivial group, and hence phi is 1 to 1. When kernel becomes the trivial group, then phi is 1 to 1. Trivial group means this one, not the other one. Okay, that is also I think called trivial. G itself is a subgroup of G. Okay, so this trivial subgroup. So that means since phi is a 1 to 1 homomorphism, it's an isomorphism, and phi is onto. That is, phi is an isomorphism of G onto G. So this completes the solution. Next exercise 3. Let G be a finite abelian group of order O of G. Finite abelian group order O of G. Order is O of G because that's the notation we are using for order, and the integer n is relatively prime to the order of g. There is some integer n that is relatively prime to the order of g. Prove that every element g in G can be written as g equal to x to the power n for some element x in G. Okay, so n is some integer relatively prime to the order of G. N may be negative also. However, n may be positive also. When n is positive, this exercise tells us effectively that every element in the group has an nth root x. Okay, so that way also we can interpret, and hint is given. Consider the mapping defined by phi of y equal to y to the power n, and prove that this mapping is an isomorphism. Okay, we are not going to follow the hint exactly. We will do something slightly different. We in fact are not going to define any mapping. We will try to directly show that G is actually equal to x to the power n for some specific x. We start off the solution by using the hypothesis that n and order of G are relatively prime. Since these are relatively prime, we have n alpha plus order of G times beta equal to 1 for some integers alpha and beta. Now G can be written as G to the power 1 by the definition of integral powers of group elements. G to the power 1 means G. Now in place of this 1 we can write n alpha plus order of G times beta, and using the rules of exponent that is true in any group, this can be written as G to the power alpha whole to the power n times this by the second corollary to Lagrange's theorem. This is equal to the identity element of the group. Hence, G becomes equal to this. That is G equal to x to the power n, where x is the element G to the power alpha in G. So every element can be written as some nth power of some element. Okay, then exercise 4. It has two parts. A. Given any group G, and a subset U of G, let U hat be the smallest subgroup of G which contains U. Prove that there is such a subgroup U hat of G, and in fact such a subgroup has a name also. This is called the subgroup generated by U. So that is part A. And in part B, we have an extra hypothesis. If G inverse belongs to U for all elements G in G and U in U, then prove that U hat is a normal subgroup of G. Okay, so we start by solving part A. Let S be the collection of all subgroups of G containing U. So in S the elements are subgroups of G that contain U as a subset. Note that S is a non-empty collection because G belongs to S. Since G itself is a subgroup of G containing U, so G is an element of S, and as a consequence S is non-empty. So since S is a non-empty collection, there is no problem in considering the intersection of all the elements of S. Since every element H in S is a subgroup of G containing U, T is also a subgroup of G containing U. For two things, there are two things here. The first is that since T is an intersection of a number of subgroups, which we have already seen, itself becomes a subgroup of G. So that is why T is a subgroup of G. Besides that, since every H contains U as a subset, so their intersection will also contain U as a subset. So T contains U as a subset. So T is also a subgroup of G containing U. That is, T belongs to S. T itself is an element of S. Note that T, because it's the intersection of all the elements of S, it will be contained in every element of S. T is a subset of H for every H in S. Thus, T is the smallest subgroup of G that contains U. So such a thing exists. That is, T is nothing but our U hat. Okay. Now to prove part B, we actually need to show something more about U hat, more than the definition it has, namely the smallest subgroup of G containing U. We want to know something about how the typical element of U hat looks like. Now, for that we have to consider two cases. One in which the subset U is actually is actually the empty set, and the other is that the subset U is non-empty. Let U be the empty subset. Since the trivial group consisting of only the identity is a subgroup of G that contains the empty set, so we have U hat equal to E. Why? Because you see, this is the smallest possible subgroup of G, and that itself contains U. So clearly it's also the smallest subgroup of G containing U. So that's why, by the very definition of U hat, in this particular case U hat is equal to E. Next, let U be a non-empty subset of G. Define a set, a subset of G like this. U1 to the power K1, U2 to the power K2, Un to the power Kn, where n is a positive integer. U1, U2, etc. These are elements of U, and K1, K2, etc. These are integers. Any integers. Okay, the ki's, each one of them may be positive or 0 or negative. They are any integers. So clearly, since we are using elements of U, so after all everything here is happening inside G. So this is a subset of G. Moreover, it is non-empty. Because why? Because U itself is non-empty now. Since U is non-empty, we have this also to be non-empty. Our aim now is to show that this is actually a subgroup of G. So for that we will consider two elements from this subset and then try to show that it's a subgroup by using those two elements. So let V1 to the power say L1, V2 to the power L2, Lm belong to this. where n and m are positive integers, the ui's and the vj's are all coming from u, and the ki's and the lj's are any integers. Okay, then what happens when we calculate this? If we can show that this element is again in this subset, then clearly this subset will be a subgroup. Using all the rules of exponent as well as the rule for taking the inverse of a product, using all those things we get this. Because we are taking inverse, the order will get reversed. Minus Lm Pm minus 1 minus Lm minus 1, etc. V2 minus L2 P1 minus L1. Looking at this product, you can see that this is again a product of integral powers of elements of U. So that means this belongs to again the subset. Thus, this is a subgroup of G containing we cannot say containing U. For that we have to argue separately. We have managed to show that this is a subgroup of G. Also, clearly U is contained in this. Why? Because if you take any element of U, say you take U belonging to U, then U can be written as U to the power 1, which also has this form. In this case, n is 1, k1 is also 1, and u1 is U. So that's why this belongs to this, and that's how we get this inclusion. So this becomes a subgroup of G containing U. In other words, this is also in the collection S. So we can write like this. Hence, this belongs to S. Which implies it will contain the smallest subgroup of G containing U. Now, let H belong to S, that is H is any subgroup of G containing U, containing the subset U. Then U is contained in H, and so this is also contained in H. Why? Because you see, how does the general element of this subgroup look like? Like this. That the ki's are integers and ui's are coming from U. Now since the ui's are coming from U, so the ui's are in H, so their integral powers are also in H, and the product of those integral powers is also an element of H. That means this general element of this subgroup is again in H, and that is why this subgroup is contained in H. But this implies what? That this is contained in the intersection of all the elements in S, which is nothing but our subgroup generated by U hat. So now you combine this inclusion and this inclusion. So U hat is equal to U. So in this way, when U is non-empty, we have in fact shown how the elements of U hat look like. They are products of integral powers of elements of U, finitely at a time, of course. Now we are ready to solve part B. In part B, we are given that condition that if you take any element of G, in fact let's just start by writing that. We will write the condition but in a slightly different manner, as an implication. If G belongs to G and U belongs to U, then this implies GU G inverse belongs to U. Our aim is to show that the subgroup generated by U is a normal subgroup of G if this condition is true. If U is empty, then the above implication, this one, is vacuously true, because in the hypothesis of this implication, the hypothesis is false because U is empty, so we cannot choose any element from U. So that's why the implication is vacuously true. That means whatever is said in part B is after all true, although vacuously true, it is nevertheless true when U is empty. Also, in this case, what is U hat? We have already determined that when U is empty, U hat is the group consisting of the identity element, and we know that this is a normal subgroup of G. So in this case, at least we have proved part B. Now assume U to be non-empty. Then we know that U hat is this. So now we know how any element in U hat looks like. Let G be any element in G and this be any element in U hat, which we are able to do because of this thing we have already proved in part A, where n is a positive integer the ui's are in U and these are integers. Now our aim is to show that U hat is normal. So we form this product. Which can be written like this. The G inverse G's that are appearing inside, not on the boundary, they cancel out, leaving us with this. It's just like that thing. Gxy G inverse equal to Gx G inverse G by G inverse. It's like that. Now this can be further written like this. Gu1 G inverse to the power k1 Gu2 G inverse to the power k2, etc. Gun G inverse to the power kn. The question is how, and the answer is it's a fact. The fact that you can prove, I don't think we have proved this. I leave it to you. Okay, you prove that this is equal to this irrespective of the integer k1. K1 can be any integer and this will still be true. The way to prove this, of course, is this. You prove it when k1 is greater than or equal to 0 by induction on k1, which is not very difficult. And then using the fact that this is true for k1 when k1 is a non-negative integer, you prove the case where K1 is actually negative, which I believe you can do. It's not unduly difficult if you follow the steps properly. You first show the case K1 greater than or equal to 0 by induction on K1, then use that case to prove the case where K1 is a negative integer. With the help of that result, we have been able to write the product like this, and this now belongs to this. Why? That is coming from our hypothesis, this implication which is the hypothesis, because since all the ui's are in U, so GUI G inverse will also be in U. So again, this thing is a product of integral powers of elements of U. These are the elements of U now, and hence it belongs to this, which we have already shown is equal to U hat. Thus, U hat is a normal subgroup of G. And in the course of solving this exercise, we have in fact got a nice another characterization of U hat in terms of the elements of U. Then exercise 5. Okay, now we are going to, so that was a general subset U of any group. Now we are going to take a special kind of subset U. Let U be the subset consisting of all elements that look like this: X, Y, X inverse, Y inverse, where X and Y belong to the group G. In this case, U hat is usually written as G prime. And is called the commutator subgroup of G. It has another name also. It's also called the derived subgroup of G, which however Herstein is not using. Now there are 4 parts. Prove that we already know that since G prime is U hat for this particular U, so it's a subgroup of G. Now we have to prove that it's a normal subgroup of G. Part B, prove that so since it's a normal subgroup, we can form the corresponding quotient group G by G prime. We have to prove that this is, as a group, this is abelian. Then part C, if the quotient G by N is abelian, where n of course is some normal subgroup of G, prove that n contains G prime as a subset. And finally, in part D, prove that if H is a subgroup of G, and H contains G prime, then H is normal in G. Okay, so let us now solve the parts one by one. Because of part B of the previous exercise, it's enough to show that if that condition turns out to be true for this particular U, namely that if you take any element from G and any element from U, G and U, small g and small u, then G inverse is again in U, then automatically by part B of the previous exercise, G prime will be normal, and in fact that's what is going to happen. Let X, Y and G be any three elements in G, then what about this product G inverse, where U is this? This can be written as Gx G inverse times Gy G inverse times Gx inverse G inverse times Gy inverse G inverse. So the G inverse G's inside, they cancel out and we are left with Gx, this one is not there, Y, X inverse, Y inverse, G inverse. That means this one. And this becomes equal to Gx G inverse Gy G inverse. If you look carefully, this one is Gx G inverse whole inverse. When you take the inverse inside, the by our rule for taking inverse of a product, the order changes. So that means we first have the inverse of G inverse times the inverse of X times the inverse of G. Inverse of G inverse is G times inverse of X times inverse of G. Just like that, this last one becomes Gy G inverse whole inverse. Now you look at this final product, which is some element times some other element times the inverse of that some element times the inverse of that other element. So this belongs to, it has the form to be in U. So it again belongs to U. So by part B of the previous exercise, U hat, which is the commutator subgroup, is normal in G. So by part B of the previous exercise, is normal in G. Next part B. Here we have to prove that G by G prime is abelian. This we will show directly by taking two elements of G by G prime and showing that they commute. Let G prime x, so the elements here will be cosets of G prime, and G prime y belong to G by G prime. We have G prime x, G prime y. So this is equal to G prime xy, and now this can be written as G prime x y x inverse y inverse y x. You see, y inverse and y cancel out. After that, x inverse and x cancel out, and we are left with xy. Now since xy x inverse y inverse is in G prime, because it's in that U and U is contained in G prime, so that's why this is equal to G prime yx, which becomes G prime y G prime x. In brackets we write, note that x y x inverse y inverse belongs to G prime. So these two elements, they commute, so that's why, hence G by G prime is abelian. Next part C. If G by N is abelian, prove that N contains G prime. Okay. Let x and y be any two elements in G. Since G by N is abelian, we have nxy equal to nxny, that is equal to nynx, and that is equal to nyx. This implies what? xy times yx inverse belongs to n, or xy yx inverse is xy x inverse y inverse belongs to n. Okay, so U, which is x y x inverse y inverse, where x and y are in G, this is contained in N. So that means N is a subgroup of G containing this set. So the subgroup generated by this set, which by definition is the smallest subgroup of G containing this set, will be contained in N. Hence, N contains the subgroup generated by U, which is G prime. So that's how we get this inclusion. And finally, it is given that H is a subgroup of G that contains G prime, then we have to prove that H is normal in G. Okay, so the hypothesis is already given. We already have the statement that H is a subgroup of G that contains G prime. We now have to show that H is normal in G. So let G belong to G and H belong to H. We have to show that GH, G inverse, belongs to H. Note that GH, G inverse can also be written as GH, G inverse, H inverse times H, which belongs to, now you see GH, G inverse, H inverse is in G prime because it is in that subset U. So this belongs to G prime and H of course belongs to H. However, this is contained in H since H contains G prime. So that just shows that GH, G inverse belongs to H. So H is normal in G. So that completes the solution. Then exercise 6. If N and M are normal subgroups of G, prove that the quotient N divided by, N by N intersection M is isomorphic to Nm. Oh, actually it's the other way. It does not matter because isomorphic, this relation is symmetric. Nm divided by, I keep on saying divided by, it's not divided by, it's by n. Some nocturnal birds are disturbing. I hope the disturbance isn't too much. Okay, so we now have to prove that these two quotients are isomorphic to each other. Now, first of all, let us try to see that these quotients actually make sense. when n and m are both normal subgroups. In fact, let's just write the solution and then we will see. Since m is normal in G, and m is contained in Nm, the quotient Nm by m makes sense. Since m is normal in G, so Nm is a subgroup, because you see we have proved this in exercise 3 of section 2.6, that the product of any subgroup and a normal subgroup is again a normal subgroup. Is again a subgroup. Section 2.6. So by this exercise, Nm first of all is a subgroup, and since it's given that m is normal in G, so in particular m will also be normal in Nm. Moreover, since it's contained in Nm. Why I am saying that is this. You see, this is our G, this is m, and this is Nm. M being normal in G means what? If you take any element m from M and any element G from G, then this element GMG inverse is in M. Now in particular, if your G is coming from inside Nm, then also the same will be true. This will belong to M, and all of these are happening because M is contained in Nm. So that's why Nm is M is normal in Nm, and that is why this quotient actually makes sense. So that is one thing. Another thing is that since N and M are both normal subgroups of G, first of all, N intersection M is a subgroup of N, and normality of both N and M in G implies this intersection is normal in N, just like M is normal in this. So this quotient also makes sense. We now have to prove that these two quotients are isomorphic to each other. So for that, we are going to define a function. Define a function phi from N to Nm by M by Nm by M, okay, by phi of N equal to Mn. Note that since N is coming from N, and just like M, N is also sitting inside Nm. So n belongs to Nm. Okay, being in N also means N belongs to the larger group Nm. So that's why this is actually a right coset of M in Nm, because this N is coming from Nm and the function is well defined. So that's what I think we have written here. Yes. Note that phi is well defined because N is contained in Nm. Also, phi is a homomorphism because M is normal in Nm. Ontoness of phi is also clear. Oh wait, is it that clear? I mean, is it that obvious and immediate? Let Mk belong to Nm by M. Then K belongs to Nm, and so K is equal to Nm for some N in N and M in N. Now Mk can also be written as Km because M is normal, so this right coset is equal to this left coset, and K is Nm. Now since this M is in M, so it will vanish inside M and we will have Nm, okay, which can also be written as Mn because M is normal, and this becomes equal to phi of N. So any element in the second group has been written as phi of an element in the first group. Thus, phi is onto. Finally, so we have shown that phi is an onto homomorphism from N to Nm by M. Finally, one can show that the kernel of phi is actually equal to the subgroup N intersection M. This part is left to you. In fact, let me just briefly say why this is true. You take any element in the kernel, that element N should give you the identity element of this quotient, which is M. Now by definition this is Mn, so Mn should be equal to M. That means n should belong to M, but n is already coming from n, so n will belong to both M as well as n, hence n belongs to their intersection. The converse also can be similarly shown. Hence by, so now we can use our standard theorem 271. By theorem 271, n by the kernel of phi, which is an intersection M, is isomorphic to Nm by M. So that's how we achieve the isomorphism, and this completes the solution. There are of course many other exercises that we will have to solve, but let's end the video here itself. We will continue in the next one. So that's all for tonight in group theory. This is me, Lucifer, from a mathematical room. Have a nice night.